Welcome back to Chem 330. This is the second video in week 5, and this time around I want to teach you one more foundational concept before we move to stereochemistry, which is going to be a chunk of material that will stretch over at least a couple of weeks. All right, and what we have done so far is learn all foundational materials that's necessary to handle stereochemistry. All right, and this is the last piece of information that you would need to know. All right, and that is, given a formulae, we learned how to calculate double bonds. Right now, that is the case when your compound does not contain any other element besides carbon and hydrogen. Okay, now what if your compound contains halogens or oxygen or nitrogen? Okay, now if you remember from our earlier discussion, okay, all halogens, fluorine, chlorine, bromine, iodine, they all can only have maximum of one bond. Now that ties back to your general chemistry, and if you've forgotten, we're not going to dwell too much into it, but you know, the fact is they can only have a one bond maximum. Okay, on the other hand, oxygen can have a maximum of 2 bonds. Why is that? Because oxygen itself is bonded to another oxygen through double bond. So whenever it makes a bond with another element, it's the same deal. So an oxygen can bind to a carbon on one side and a hydrogen on the other, or an oxygen can be in between 2 carbons, right? Or a carbon can be directly attached to an oxygen through a double bond. In all these cases, you see the oxygen itself contains only 2 bonds, right? Now, nitrogen, on the other hand, if it combines with another nitrogen, can have a maximum of 3 bonds. Okay, so whether it's combining with another nitrogen or if it combines with another element, it's the same deal. So nitrogen can combine with 3 hydrogens, okay, and that's your liquid ammonia that you use in your daily household items, right? You can see nitrogen's got 3 bonds. What if it combines with a carbon? Well, it's the same deal. It can combine with 3 carbons, okay, but it can't have more, or it can combine with a nitrogen and a carbon and 2 other hydrogens, or the combinations thereof. But either way, whatever you look at it, in all these 3 cases, or there's 4 cases, including the nitrogen itself, the number of bonds a nitrogen can make is 3. There is, however, a quaternary nitrogen, but we don't want to get into that now. All right, I'm just keeping it to the general trends of all these elements. Okay, so let's say, what if we have a formula that has this, and I ask you to do 2 things. Calculate the double bonds, dB, and write at least 3 isomers. Okay. Now, before you write isomer for any given formula, you have to determine whether this compound has, in fact, a double bond, triple bond, or single bonds. Right now, the way you do it would be, I'm going to get a different color and block this portion here so that I don't get into this region. All right. With that said, let's go back to maybe a black. All right. The way you do it is, when you have your formula contains carbon, hydrogen, and then halogen, okay, to determine the number of double bonds, well, that's the way you should do it, because there's no other way around it, is you gotta have, when your compound contains, when your formula contains a halogen, okay, a halogen, which is either fluorine, chlorine, bromine, or iodine, then you temporarily add hydrogen. You temporarily add hydrogen to the formulae. Why do I say the word temporary? I'm going to actually highlight it, okay, with a different color, because you're not permanently adding hydrogen. What if you do? Because you're changing the identity itself. We're doing all this purely for the sake of math. Okay, we are going to do some math, and it's not going to be very intensive math, but we are going to do some math. And what exactly are we going to do? Well, I just stated here, when your formulae contains a halogen, then you temporarily add hydrogen to the formulae, right? So what I'm going to do is, this is always my given, okay? This is my given. So I'm going to add hydrogen to the given formulae, so it becomes C5H12Br. Now we do have to, so this is given. This is the new given, okay? And then let's go get our different color. We have to find the parent molecule, and whatever be the element that's attached, the only way we find parent is using the general formulae for an alkane. It doesn't matter what the given compound is, whatever this element is, the parent is always found using the general formulae of an alkane, and N stands for the number of carbons in the given compound. And if you substitute 5, that'll turn out to be C5H12, right? Good. So what does that mean in terms of how the math is going to work out? So let's go get our blue. So you write the parent at the top, right? And you write your given, the new given compound. Well, you don't need to write technically the, so this is the parent, okay, and this is the given, okay. You don't need to write the Br, just subtract them, and you notice there are no hydrogens left in the molecule. What does that mean? When you divide, you always divide by 2, because there's no hydrogen difference here. That means our molecule contains 0 double bonds, right? Now, let me go ahead and erase some of this so that I can actually draw some of the isomers here, okay? This is generally the way you calculate your double bonds. If you remember our lesson back to when we calculated double bonds in an alkene or alkyne, this is exactly the way we did. We always use the general formulae of an alkane to calculate the parent compound. So what does it mean? That means you go back to your actual formula, which is C5H11Br, right? Now keep in mind, we added the hydrogen temporarily if it is an halogen to determine the molecular formula. All right, with that said, now let's go write our 5 carbons. 5 carbons. And you can just put the Br anywhere you like. Okay, so that's 1. And if I put it on the second, that is another isomer. And if I put it on the middle, then that's another isomer. I only have you write 3. So you can think of other combinations that might be right, but I'm only writing the first 3 that came to my mind. Okay, are probably the easiest ones. So if you add, whenever you write isomers, you must always go back and check to make sure you have the right number of carbons, right number of hydrogens, more importantly, right number of bonds. Okay, because that's what I've noticed in some of your work is I think you're so worried about getting the isomer right, you forgot to count the number of hydrogens and carbons you have. You end up having too many carbons or too little carbons, too many hydrogens, or too little hydrogens. There we go. This 3 structures matches the statement here. We clearly prove there are no double bonds in our compound, which matches the given structure of what we have here, right? So what if we have a compound that contains, say, oxygen, okay? I believe I did say C6H12O. Okay. When you have oxygen, you don't make any, actually, you don't add or remove hydrogens. Okay, that's what I meant to say. When you have oxygen in your formulae, okay, neither add or remove hydrogens. Now again, we're not permanently removing or adding hydrogens. We're just doing that to figure out our math so we can match it to the parent compound. So let's go get a different color. So this right here, C6H12O, is our given, right? We're going to leave it as it is. We're not going to do anything to it. And then we are going to get our parent, which would be, again, we use the general formula of an alkane, CnH2n plus 2. And N is the number of carbons in the given compound, so that'll be C6H14. So that's your parent compound. How does the math work? Not much different than anything we've done before. So C6H14, okay? And C6H12. Again, you don't need to write the oxygen in the picture because it's just going to throw some of you down. And then let's go get a different color. All you got to do is subtract, okay? The number of carbons would probably cancel out, and then your hydrogens would be 2, and you always divide by 2, which suggests there is one double bond. Now keep in mind, when we say double bond, every compound that we've discussed has a sigma bond. That's the bond that connects every carbon. If you have an extra one, which we call it pi bond, so that means your compound contains one pi bond. That's what one double bond means. These two together is called a double bond, but what we're really seeing is we have one pi bond. That's what we're really saying. I think I've explained that before, even when I explained it. So I'm just going to draw a couple of structures. I don't want to draw too many isomers here. Remember I said oxygen can, so we have 6, right? So let me make it easy on you by showing something that I showed when I explained the property of an oxygen. Well, that's one isomer right there. Well, you want one more? Let's go. Put the oxygen here. You want one more? It's even easy. Put it all the way between this. There it is. We have 3 where the oxygen is sandwiched. That's 3. I mean, you can think of as many combinations as you want. What if I want one like this? Well, if you have thought of this, then 4, 5, 6. And I said carbon can also be attached to oxygen through a double bond. In that case, if I go back and fill it with hydrogens, it'll be CH3, CH2, CH2, CH2. Nothing has changed in terms of your learning of how we accommodate our hydrogens to carbons, okay? Nothing has changed, okay? If you believe that somehow something has changed, that is not right, okay? Because all we are doing is learning the idea of isomers from a different perspective, because I'm trying to get you to have all the foundational knowledge at your hand, because it would be difficult to go back. I can cite where we have learned these, but you should always know. So there's one. And then you can also think of, I did say that you can also have a OH. That means the double bond must be somewhere in the carbon area. Now in this case, now what have we missed here when we did it this way? I know I made a mistake, which is the structure clearly said the compound has a double bond, right? But I didn't have the double bond by putting it this way. So what I'm going to do is probably get rid of this each time, okay? That means I should have had this, right? And then same thing for here. I guess I can put it here. So that would be CH double bond CH, right? Or I could have had here, you know, there's so many options that you have, but you have to make sure that you addressed, or at least you came back and fulfilled the purpose that you started with, okay? Okay, that's 3, 5, 6. Okay, got it. So this should have been this long bond. You see, if I decide to use the oxygen as a sandwich, then the double bond must be within the carbons. If I attach the oxygen itself as a double bond, then I've already fulfilled the one double bond requirement, right? Now, keep in mind, whenever oxygen is sandwiched, okay, that type of compounds are called ether, extremely flammable, okay? Whereas when a carbon is part of an oxygen and a double bond, it can be an ether or a ketone, which we don't need to focus. Again, I'm just giving you that information. You don't need to remember this piece of information here. We would learn all this again one more time, at least not this part, but when it comes to ether and ketone, when we learn ether and ketone, okay? So that's with oxygen. Now, what if we have C8, H7, and nitrogen? When we have nitrogen, you must subtract the hydrogen. Subtract hydrogen when you have nitrogen, okay? Now, I am only showing you a situation where there's only one nitrogen or one oxygen or one halogen. If you have 3 nitrogens, then you have to subtract 3 hydrogens. If you have 4 bromines, then you have to add 4 hydrogens, okay? So I'm not showing all those here because it's the same logic, all right? And then, so basically, again, you're not subtracting the hydrogen permanently, you're just subtracting to do the math. So what does that mean in terms of what would it look like? So it will be C8H6N, right? This is our new given compound. This is temporarily new given compound. And let's go get our parent, which would be, again, CnH2n plus 2, right? Right? So that means we got C8, so that'll be C8H18. That's our parent. We always use the alkane general formulae for obtaining the parent. Now we have this information. Let's go do our math. So C8H18 is the parent, and C8H6. Again, you don't need to include the nitrogen in the mathematical portion, so this cancels out, which leaves us with 12O by 2 is 6. Okay. Now, if you remember, nitrogen forms triple bond with itself, or it can attach. It can only have a maximum of 3. It can have, you know, when it's a nitrogen, it can have 3 separate carbons attached to it, or it can also be this way, right? There's 3 different ways this can exist, okay? Or it can all be hydrogens on either side. Either way, now what does this mean is our compound contains 6 double bonds, right? So let's go get a different color. So that means I'm just going to show one. You can see if you can come up with the remaining 2. There's probably more, but again, I will not test you more than 3 to 4 isomers in lieu of time when you take a test. All right, so that means our compound contains 8 carbons. Now, we have not quite learned benzene. All this would be even more simple in terms of isomers if we had learned benzene, but we have not. So we're going to restrict to what we have learned. So 8 carbons here. And then for now, I'm just going to go with Cn as one of, you know, I'm going to put the nitrogen as if it's attached to the carbon. What does that mean? I've already used 2 of the pi bonds out of the 6. So which means I am going to go put 1 here, and then 1 here, 1 here, okay? And then I might actually, you know, in the process, I still have 2 more two more pi bonds, right? So what I'm going to do is make one of them is triple and triple. So that means this is 2 pi, this is 2 pi, and there's 2 pi here, right? That is how I accommodate my 6 pi. So you can, double bond also really means that you can have 2 pi. So you can have 6 pi. So this is one of the isomers. So you can also do it as 5 carbons, right? Sorry, 7 carbons, and make one of them as your substituent. Cn is your substituent. Now the nitrogen, I'm planning to attach it through the carbon. So I've already got 2 pi bonds here, and then I can put one more here. I will make this 4, and then I will put one here, and then I'll put one here, and maybe make one of it as a triple, maybe make it as a triple. So that'll be 2 pi. This is 2 pi. No, I'll just leave one of them as just a double bond. Okay, so that's 1 pi, 4 pi, and there's 1 pi here. So that is, again, I've not filled the hydrogens in, but you see I got the 6 pi's back. So it's the 6 pi here. This one. So this if writing this particular structure is a little difficult for you, just bring up your questions during class. But that's how you determine double bonds and write isomers for compounds containing nitrogen, halogens, and oxygens. All right, so that's a one long video for week 5, and then I would probably wrap up week 5 with this material, and then in the next video, we will start to learn stereochemistry. And as I said, it's a pretty vast concept, and we may not be able to learn everything about stereochemistry, but we will learn a good chunk of stereochemistry. It will probably stretch across week 6 and 7, because I don't think I can just cover everything in 1 or 2 videos or in 1 week. All right, so that wraps up week 5, and so I'll see you all with week 6 video. Stay tuned. Bye-bye.